Welcome to the first video in Introduction to Quantum Field Theory. I am basing this series off of the book No Nonsense Quantum Mechanics. It's a very good book, in my opinion. There are some typos in it, but it's not a big deal. They're pretty obvious. And the first video here will be on tensors because they are kind of important. They're the backbone of quantum field theory. The standard approach to quantum field theory uses a tensor formalism. And in reality, tensors are just a generalization of matrices, so they shouldn't seem too foreign. Let's first talk a little bit about rank, because rank is pretty important. So in general, you can have rank 0. So if you have a rank 0 tensor, then you have essentially just scalars. And these can be more accurately written as rank 0, 0. And they just describe scalars. So zero-dimensional tensors. There's also rank 1, or there are also rank 1 tensors. And these are contra slash covariant. So contravariant or covariant vectors. And these are written for the contravariant, a superscript mu, or can have a subscript mu. These are your rank. I just realized that 0, 0, these are your rank 1, 0, or 0, 1 tensors. So a rank 1 tensor is either rank 1, 0, which is contravariant, or is rank 0, 1, which is covariant. We'll see what the difference of contravariant and covariant is in a second. Then rank 2, which for now we're only going to be dealing with rank 2 vectors in this series, so we only need to know up to rank 2. These are essentially just matrices. And you can have, for example, we'll do G mu nu, G superscript mu nu, G nu mu, G mu nu. And there are 3 possibilities for the type of rank, or the subclassification of rank. You can have 1, or you can have 2, 0, 1, 1, 0, 2. This qualifies as 0, 2. This qualifies as either of these, and 2, 0 is either of these. And it's not super intuitive what the difference is between these off of first bat, because contra and covariant will make the most sense as with vectors, but we'll see how they all relate to each other, and hopefully after seeing how they relate to each other, it makes more sense what they actually are. It's hard to define without seeing them in context. So these are the ranks of the tensors we're going to be dealing with. And the way that a contravariant vector is kind of defined is as a column matrix. So in this video, in this video, we'll be using in this video, we use 1 plus 2D spacetime. Just gonna put that there. So there's the first component, the second component, and the third component. And this is how a contravariant vector is defined. It's just a column vector. And this is related to a covariant vector, where if you have a covariant vector, then it will be a row vector. Here. So contravariant vectors are just column vectors, and covariant vectors are row vectors, but they have a relative minus sign. The relative minus sign comes from the fact that we have 2 dimensions of space and 1 dimension of time. So I'm assuming you have a little bit of a background in relativity and you understand why you need a relative minus sign. And these vectors are related by the metric tensor. G mu nu, and we'll see that it's actually equal to these, that the metric tensor 2 or 0, 2 and 2, 0 rank are actually the same thing. The way that they are related to each other then is a superscript mu is equal to a nu g nu mu. Sorry, that is incorrect. Mu nu. And this is the same thing, or is it's not same thing, but it is a logically equivalent statement to a mu equal to g mu nu a superscript nu. So it's saying that the if you have a covariant vector and you apply the metric tensor to it, you get a contravariant vector. And if you have a contravariant vector and you apply the metric tensor to it, you get a covariant vector. And these both define, you have G mu nu. This will form a 3 by 3 matrix, 1, -1, -1. You might wonder how I know this. Well, we're about to see below. I'm going to write it. I'm going to write it out. And it turns out that this will be the same. Okay, let's move that over here. Okay, there we go. Finally wrote that. It's the same as having A naught, A1, A2, A naught, negative A1, negative A2, 1, 0, 0, 0, -1, 0, 0, 0, -1. And this is the same or logically equivalent to having this equal to this. And so these tensor equations correspond to these matrix equations. So tensors take advantage of the fact that these follow, or the way matrices behave follow patterns. And so you can, if you have something that is contravariant and covariant, you can kind of cancel these out. And this G then modifies the A to have superscript. So the G, the mu's cancel out if they're top and bottom, and then the mu is what's left. So it goes from A nu to superscript mu. And likewise, something happens here. The nu's cancel out, and the mu is the only thing left. So just hover over these so you can get an idea. Okay. Now let's talk about some important tensors. These are tensors that we will use at various points throughout this series. The first one is the derivative. So if x superscript mu equals g, sorry, x nu g mu nu. So if this is the position, then the derivative with respect to position is either you have the contravariant derivative, which is defined with respect to the covariant. So the contravariant derivative is defined with respect to the covariant position. Or you can use the covariant derivative, except I wouldn't really call it the covariant derivative because that means something else technically. You get mathematicians and physicists repeating names for things, so just say the derivative with respect to the covariant position, or the derivative with respect to the contravariant position. Okay, and then there's also what's called the Kronecker delta. That is defined as delta mu nu, which is equal to delta mu nu, which is equal to delta nu mu, which is equal to delta mu nu. What are these things all equal to? Well, it's equal to 1 or 0, and they are conditioned. These are conditioned statements. If mu equals nu, and if mu does not equal nu, then they are either the value of this is either 1 or 0, but this is, recall, a matrix. So in reality, this is the matrix that has ones along the diagonal and zeros everywhere else. So essentially, It's like the identity matrix. Now, there's also the Levi-Civita symbol, and that is epsilon, then you can have JKL, which is whatever matrix that satisfies these following properties. This is if it is cyclic, is anti-cyclic, and this is if an index repeats. So the Levi-Civita symbol is actually a matrix that has entries that satisfy this. So at parts where the entries of the matrix, the like position, rather, just realized that this is a tensor, but it is actually a a rank 3 tensor, not a rank 2 tensor. So it's not a matrix, but either way, it's not really important. You don't need to visualize this as anything. This is just capturing the idea whether things are cyclic, anti-cyclic, or if an index repeats. This, if you're familiar with geometric algebra or the exterior algebra, then you can imagine this like if you have a bivector, and then if you have the reverse of a bivector, and then if you have a vector wedge itself. A vector wedge itself is like an index repeating, so it becomes 0. There's also in, so this is in 1 plus 3 dimensional space-time. There is the Minkowski metric, which is written eta mu nu, which is equal to eta mu nu, and it is a 4 by 4 matrix, 1, -1, -1, -1, and then zeros everywhere else. So these are going to be the most important tensors in this series. This will be used whenever derivatives are involved. This will be used to kind of do a change of basis, because right here, this, not change of basis, but change of index, because you end up with properties like this. A mu, uh, mu nu, it gives you a nu. So if you have a vector and you want to change the index mu to be an index nu, then that's what this does. It just swaps the indices. So you still have the same vector, but now you're describing it with different indices. Levi-Civita symbol will just encode cyclic and anticyclic things, like cross products, for example. And the Minkowski metric will serve the role of the metric in these equations. But as these were describing 1 plus 2 dimensional space, we basically have these, but in 1 plus 3 dimensional space. So the Minkowski metric. So let's talk about the inner product of vectors real quick. It's pretty simple. You have a mu, which is equal to a mu. This is a scalar. This is scalar, a real scalar. And this is the inner product. This works because a mu is equal to g mu nu a nu. So you can kind of imagine this as a a mu, which is just equal to a mu, or what do you call it? Blah, blah, blah. Forgive me. Let me rewrite this. A mu is equal to g mu nu a mu, which is equal to 1, -1, -1, 0, 0 times a naught, a1, a2, a naught, a1, a2, which is just a naught, a1 minus a2, a naught, a1, a2, which is equal to a naught squared minus a1 squared minus a2 squared. Oh, I want to make something clear here that you may be wondering how are these two things equal? Because this is a row vector times a column vector, and this is a column vector times a row vector. And in general, matrices do not commute, and so you cannot get the product of a column vector times a row vector as being the same as a row vector times a column vector. Well, the thing is that in the tensor formalism, these represent the indices and the objects themselves. So these, you can cycle these here. You can rearrange these. And it's only when you actually work with the matrices that you need to care about the ordering, but you don't need to care about the ordering in the products here. For example, while I had to write the column or the row vector here and the column vector here, I could have written this on this side and this on this side. It doesn't matter. The reason why I presented things the way I did is to show conceptually what these tensors are representing and make the connection easier to make. Now, you can also perform rotations, rotations, boosts on vectors or of vectors. So if you have there exists always some tensor or matrix rotation matrix such that it will map some vector, and you could use either covariant or contravariant in the definitions here. They're interchangeable conceptually. And it maps to some transformed vector, which would be equal to this. So that would be the form of a rotation. And this is also the way a boost would work. And if you were to consider some combination of a boost and rotation, then that would be how a Lorentz transformation would work. And so while you can transform vectors, you can also transforming, or you can also transform tensors. And the way that that works is there always exists, oh, that's not what I needed, lambda mu alpha, and actually I'll do this, mu beta, lambda alpha nu. There always are um, Lorentz transformations, which could just be pure rotations, pure boosts, or combinations, such that some general tensor will map some general tensor mu nu will map to a new tensor, and it's equal to mu alpha beta mu alpha beta. So it's interesting that a tensor just behaves like two vectors. So you first transform it like one vector, and then you transform it again. So this has been a summary of the tensor mechanics that are used in quantum field theory.